In this video we consider the characteristic roots and the stationarity condition in an ARP model. We use an AR2 model to illustrate the main results, and then we generalize them to an ARP model. The AR2 model is given by yt equal to a constant theta1 yt minus 1 plus theta2 yt minus 2, and finally we have epsilon t. We make the usual assumptions, t equal 1, 2 to capital T, so that's our sample size. We assume epsilon t is IID, mean 0, variance sigma squared, and finally we assume that the initial values are given. Next we define the Lac operator. So the Lac operator L multiplied by yt is equal to yt minus 1. And second, consider delta yt. That's the first difference operator, and that's equal to 1 minus L times yt, which is just yt minus 1. So this is just the first difference. We can use the Lac operator to rewrite our model for yt. We rewrite all the yt terms on the left hand side like this, and that's just equal to the constant plus epsilon t. Now we use the Lac operator, and we can write this as 1 minus theta 1 L minus theta 2 L squared multiplied by yt, which is then again the constant plus epsilon t. Now let's define what we call the characteristic polynomial, given by theta of z, so this is a function of z, equal to 1 minus theta 1 z, theta 2 z squared. We can use this to write the equation we had up here as theta, and instead of z we have L here, the Lac operator. We multiply that by yt, and that is equal to constant term plus epsilon t. Note that we can rewrite any autoregressive model like this, and now what we want to do next is study the properties of the characteristic polynomial in order to understand the dynamic properties of the model. Note that the characteristic polynomial is a polynomial in set of order p. So here p is 2. This is our simple AR2 model. Next, we consider the characteristic equation and the characteristic roots. So the characteristic equation is just the characteristic polynomial equal to 0. This gives us 1 minus theta 1 z minus theta 2 z squared is equal to 0. We have p equal to 2 characteristic roots, z1 and z2, and they are the values which satisfy that when we evaluate characteristic polynomial in the root here, it satisfied the characteristic equation. So the polynomial evaluated z1 is equal to 0, and likewise polynomial evaluated in the second root is equal to 0. Note that we have p roots, and if p is higher than 2, then the roots can be complex. Also note that we call z1 and z2 the characteristic roots, but we could also define phi1, which is the inverse root, and phi2, which is the inverse of z2. So these are the inverse characteristic roots. We can use the inverse roots to factorize, so we can write the characteristic polynomial theta of z as, first we have the definition from before, but we could write that in terms of the inverse roots. So we have 1 minus phi1 z, 1 minus phi2 z. This is just a factorization of the polynomial. Finally, note that with p equal to 2 we could multiply the terms together and we get the following. So this is just a second order polynomial. It has 2 characteristic roots, z1, z2, and it has 2 inverse roots, phi1 and phi2. We can state the dynamic properties of the model, the stationarity condition in particular, in terms of the characteristic roots or the inverse characteristic roots. The stationarity condition says that if the inverse characteristic roots fall inside the unit circle, then the inverse characteristic polynomial given by theta of z inverse, which is an infinite polynomial, we can write that as 1 plus z1 z plus z2 z squared plus z3 z to the third power, and so on. So again, if the inverse characteristic roots fall inside the unit circle, then the inverse characteristic polynomial is convergent. That means that the coefficients c, 1, 2, 3, if we look at ci, that converges to 0 for I going to infinity. That implies that if we look at the sum of 1 plus c1 plus c2 plus c3 plus, this is an infinite sum, this converges to 1 divided by characteristic polynomial evaluated in 1, which is, in our case, is given by 1. And then we look at the characteristic polynomial up here, and we insert z equal to 1, so that just gives us 1 minus theta 1 minus theta 2. So this is the stationarity condition. If the inverse characteristic roots fall inside the unit circle, means that if we plot the unit circle here, we have 1. So this is a unit circle, and if we calculate the inverse characteristic roots and they fall inside the unit circle, that means that they have a modulus less than 1. Remember that they can be complex if we have an autoregressive model of order more than 2. If the inverse roots are in here, then the process is stationary. When the inverse characteristic roots fall inside the unit circle, then the inverse characteristic polynomial, which is an infinite polynomial, then that is convergent. And just note that we refer to the characteristic polynomial as being invertible. So invertible here just means that the inverse characteristic polynomial exists and it is convergent. Now, assuming that the stationarity condition is fulfilled, we can look at the MA representation we have from before. And now if the stationarity condition is fulfilled, we can rewrite this as yt equal to the inverse characteristic polynomial multiplied by the constant term and epsilon t. If we write it out, we get yt is equal to 1 plus c1l plus c2l squared plus c3l third power, and so on, multiplied by the constant term plus epsilon t. Note that the Lac operator multiplied by the constant term is just equal to the constant term, so we can write yt as 1 plus c1 plus c2 plus c3. This is an infinite sum multiplied by the constant term, and then we multiply onto the epsilons, which gives us epsilon t plus c1 epsilon t minus 1 plus c2 epsilon t minus 2, etc. Note that the c coefficients here converge to 0, so c 1, 2, 3, 4, they converge to 0 given stationarity, which means that the effect of shocks in the past converges to 0, so shocks only have a transitory effect. From the expression here, we can find the expected value of yt, and that is given by delta divided by the autoregressive polynomial evaluated in 1, which is equal, in our case here, to delta divided by 1 minus theta 1 minus theta 2. So that's the unconditional mean. It is constant, does not depend on t. But note that it depends on the constant term as well as both of the autoregressive parameters. That's it for now. Thanks for watching.